So we have some weight function which is takes the target x and sort of shapes or weights the y's let's say response to sort of produce the estimator. So these for partitioning estimators, these would look like that. So you have a so this guy is the cell of the partition in which x lives. So you partition the space. There is a cell in which x lives, and the weight would be 1 over, like proportional basically to 1 if xi is in the same cell as x. And so you just divide by the total number of points that are in the cell. So you just basically average all the y's that are in the same cell as x. So there are other examples we'll see. So Stone's theorem was something like that. So if you have these, let's say 5 conditions, then these local averaging estimators would be universally consistent. Universally consistent for any, basically for any distribution p on x and y. So this is the distribution, joint distribution of x and y. And we care about all the joint distributions for which y has finite second order. Then this L2 distance between the two functions go to 0. And as I mentioned, this L2 distance has, okay, I don't have the previous version of the slides here, but what this is saying is, so the L2 distance is, just to remind you, it's just the integral. It's an aggregate measure of performance. It's not pointwise. We could look at pointwise losses as well, but this is going to be, you can write d mu x, where mu is the distribution of x, so the marginal distribution of x. So that's basically the meaning of this. And then I have another expectation behind it, which is there because this is still a random quantity because of the randomness in f hat n, which is so random because of the data. So this is like f hat n of x and the data, the training data. And so there's randomness here. So when I put an expectation here, I'm taking the expectation with respect to randomness in both the training data, and you can think of this like this integral as an expectation with respect to the test data. Okay, so if I want to write it, so if you sometimes you see people write something like expectation dn, or something similar to emphasize that this expectation is respect to the training data. Okay, there's nothing, no other randomness here besides the randomness in the training data. Training data is just en. Again, I'm going to use different notations, but this is from the regression book, and some people use this as well. So this is the training data. And then this equality I can rewrite also as, let's say, expectation under dn, expectation under x of f hat n x minus f star x, where x is my test point. And so the test point is another point from the distribution, which is independent of the training data. Okay. So this inner integral is just something like that. And this iterated integration makes sense because the x and the training data are independent. So it doesn't matter. I can reorder, I can just put it just a joint expectation. I'm hoping people are comfortable with this. I can just write it simply as this. This is now taking the expectation over all the randomness, both in x and in dn. Okay. So if you write it like this, if I don't specify, if I don't say anything, I'm taking expectation with respect to all the randomness there is. So this is a deterministic quantity, and this is like this, where here the expectation is expected to be n. Okay. Just there's the dn randomness left in this. So once you play with this a little bit, you get hopefully comfortable. And let me know. Is it clear so far? Yeah. No, dn is just training data. Okay, so the joint distribution in x and y is always p. If you want to think about this, the distribution of this is p to the n. It's like the product distribution. No, mu. So, yeah, so this is like the test point. So I draw x, y pair from p separate from everything else. And I evaluate the functions on this test data. And let's say if I compare it with, let's say what you can do is that you can, if you have a function x, so a function f, you write on the test data and you compare it with y. Okay, so you can try to compute this as well. For any function, this is very, very close to this. So I encourage you to try to compute this. The key part is this part, because the rest is noise. So if I try to compute this, so minimizing this is close to minimizing this. Maybe I'll assign it as a whole problem. But that's what you want. So you want to predict the next y associated with this one. And this is a loss function for your f. Basically, you're evaluating it. What I'm doing here is instead of y, I'm looking at f star x, which is the best prediction of y given x under the population. So you can decompose that loss into this. So as an exercise, right? Something like f of x minus y squared is expectation of fx minus f star x. For us, f star x is the conditional expectation, remember, plus some other term, which doesn't depend on the f. So that's like the unimprovable part of the loss because of the randomness. So this part you can set to 0, you get there. But there's this part that's unimprovable, and so f star is actually, yeah, we can do it right now. So f star x is just expectation of y given x. Is it clear now? This is basically a conditional bias variance decomposition if you write it. Other questions? I won't write it. I want to assign it as an exercise. It's good for you to go through. And we will basically do similar things when we try to prove Stone's theorem. Exercise. Fill the gap. Questions? Okay. I'm going slowly to get used to this notation. So what we are going to do is, let me point out here, I'm going to come back later. What we usually do is, I'm going to introduce these notations to simplify. So P tilde is probability with respect to conditional on xn. So I'm conditioning on the x part of the training data. X superscript n is x1 up to xn basically combined. So I'm going to write something like that for compactness. And then I'm going to use this notation for simplicity. We could like avoid doing this, but just to simplify the notation, I'm going to put a tilde. So when I do tilde, it's just conditional expectation given the training x's. Okay. If I do the training x's, the reason why I'm doing this is because the local averaging estimators for which we have the Stone's theorem, these are dependent on the x part of the training only. So when I condition on the x, this part is going to be constant. The only randomness that's left is the randomness in yi conditional on the data. So that's what I'm going to do. So if I do this, then what you can do is, so the strategy is to first the first note that I can do something like that. If I condition, this is the conditional expectation of f hat n x minus f star x squared. This is a conditional expectation. If I take another expectation, that would just give me the loss that I want. So that would give me expectation unconditional of fx minus f star x squared. This is the smoothing property of conditional expectation. Okay, so this is a conditional expectation. If I put a total expectation outside, just removes the condition, I get this. So the loss that I'm looking at is something like this. And then the strategy is to, so just remember this. And the strategy when I try to deal with this is that because now, because this x is independent of everything else, what I'm going to first analyze is analyze this under just the deterministic point. Okay, so we're going to do this. Here it's the random point, but I'm going to first compute this. Okay, for a deterministic point, this is now, there's the only randomness that is from the training, and I'm conditioning on the xn. Once we analyze this, then whatever expression we get, we can just plug in x, random x, because the randomness in this was independent of that. So just plug in x and then take the expectation. Okay, so that's the plan that we're going to follow. Okay, so just remember this expression. We're going to come back to it. Okay, it's just the idea to first condition on xn and then evaluate at the deterministic point. This is rather simple because once I condition on, there's a conditioning on xn here. The weights are fixed, and I'm evaluating the fixed points, so the weights are really deterministic. The only randomness here is just from yi's, okay, in the training. So I'm going to come to this. Let's jump to the proof and come back. I have some, I talked about these. This is about because the way we went. So let's try to prove, and then I'm going to come back and do the examples. So local averaging estimator is something like this. Again, this is just dependent on the, only depends on xn. And then I'm going to define like a idealized version where I just pass f star through this. So if I evaluate f star at xi, this is the idealized version of yi. That's the conditional mean. If I pass it through this estimator, this gives me this estimate of the function. Somehow this is related to the bias because I can't, if I can reproduce f star exactly by these weights, then I have no bias. If this is very far from the f star, then you're gonna have a problem. Okay, so like there's some intuition for this. Right? So yi's are centered around f star plus some noise. If there was no noise, basically I would just have yi equal f star xi. So this is the noiseless version in a sense. So we have this bias variance decomposition. If you define it like that, this loss, which is just the expected L2 norm, this is the same thing as I mentioned. So the expected L2, the thing that we want to control. This is the expectation of this deviation. This is the true f. This is this reconstructed f tilde s. squared plus this term, which is actually the variance. Okay, so that's what we want to prove. So how many people know what bias variance decomposition is? Remember the bias variance decomposition? Okay, so we'll do it, and you can help me write this. But it's a very nice formula. So you can see the variance, the square of the weights come in, then we try to, the sum of the squares, we can try to bound the variance. This sigma, if you recall, sigma x is just the conditional standard deviation. Let's say sigma squared is the conditional variance of y given x equal to x, because we are not assuming this to be constant, so it stays here. Okay. Is this statement sort of clear? Let's go through the proof, it becomes more clear. So that's the notation that I have. This is the identity that I mentioned. So what we're going to do to prove this, we first look at, so fix little x, and then let's look at expectation tilde. This is the conditional on x, so this minus f star x squared. The x here is deterministic, so I'm going to write it like that. So the reason why I introduced this is because this is just a valid expectation. I can just treat it as like a regular expectation. I can do the bias variance decomposition for this. You don't have to worry too much about it. So how do we do bias variance decomposition? Let me also introduce this var tilde if you want, which is variance conditional on xn. You either have to do everything or none. Just okay. So how do we do the bias variance decomposition here? So this is deterministic here. Let's calculate maybe. Let me do first. It will help. Expectation tilde f hat. There's an n here. I'm going to drop it for simplicity. So this expectation tilde is this is summation I from 1 to n wi. You want ni, let's say. N is also like extra. And also drop this n for simplicity. Maybe I'll drop it, simplify the notation. So we have these weights. Okay. The expectation is conditional on the xn, so this is completely deterministic, so this comes out. I get summation I from 1 to n wix expectation tilde yi. So now what is this? Yeah, so this is basically expectation of yi given xi, because conditional on the x, all the x's, this is just the one that matters, and this is just f star of xi by definition. Okay. Good. How about the variance? The variance tilde of f hat x. This is going to be variance tilde of the same thing, summation I from 1 to n wix yi. The conditional on xn, these are deterministic, yi's are independent. So what would happen to this variance? Yeah, so because of the independence, conditional independence, basically. So this becomes the sum of the variances, wix yi, and this itself becomes wix star squared. This is deterministic, comes out variance tilde yi, and this is what? This is variance of yi given xi, which is, if you remember, sigma squared xi. That's how we define it. So these conditional, so let's say this conditional expectation is exactly the same. Sorry, not exactly the same. It's just the weighted sum of this. So you can see this is the way we define this. This is so the way we defined f tilde star. This is f tilde star of x. It's not exactly. It's not unbiased. The weights apply to f star xi. So if you go back up here, just evaluate this at little x. This is exactly f tilde x. So the conditional expectation of f hat x is this sum times that. So that's by definition. Let me maybe write it here. That's the way that we define things. So summation I from 1 to n, w I x f star xi. Right? And this is equal to f tilde star of x. Okay, so for example, if I take another expectation outside, this remains. So overall, this is not unbiased, at least not conditionally. So this passes through this, gives you some like a distorted version. And the whole point is that you need to choose these weights such that this bias is small. Okay, and the variance tilde is just what we showed is that this is just summation I from 1 to n, wi squared x sigma squared xi. Okay, so maybe I should open a new. So here, add a new page. Okay, that's the summary of what we did so far. I'm gonna cut this here. So we computed the expectation and the variance. Now I can ask my question. Maybe it's a different color, it would have been better. So far clear, right? So that's the conditional expectation. It's simple. So everything is sort of constant almost except yi, and then yi's are conditionally independent, and the conditional mean and the variance are just given the names. So we get that. Now how do I relate this to this quantity that I care about? So this is not exactly these, but it's related to these. How can I write the bias variance decomposition here? Maybe make it better. Okay. Yeah. So add and subtract yi's. We could do that, but it's easier to do something else for bias variance decomposition. It's easier to add like the expectation of this, add and subtract this, right? And then the cross term vanishes. That would give you the bias variance. So what you need to do, like, add and subtract this expectation. Okay. So do this as an exercise, and the cross term goes away. So if you remember what the bias variance decomposition is, you can just write it down. You don't have to redo it. So this is the expectation of this minus f star squared plus, you get f hat minus the expectation squared, which is the variance. So you get variance tilde of f hat x. That's the bias variance decomposition. So bias squared, this is like the conditional bias, the squared plus the conditional variance. So there is a step in the proof, but I'm assuming that you remember what this is. You do it once, you use it like many times. But it's basically adding and subtracting this expectation and noticing that the second term is the variance. The first term is just this, deterministic, and then the cross term goes away. So this, if you do it, the first thing that we calculated here is just f tilde s x minus f star x. That's our bias. And then the variance we also calculated, plus summation I from 1 to n wi squared x sigma squared xi. That's almost there. Now at this point, what I'm going to do is I'm going to just plug in, because this expectation, this is like an integral. And if I plug in random x, the test point in this, this doesn't affect. So we can start it with random x here because it's independent of everything else. Everything goes through and I get x here. Okay. So the whole thing goes through, even if there was a random x here. You could have started with that. I just did this like, so you have the same expression. If I do the random x, this is now a capital X. With this replaced with all the x's replaced with big X, and then I put another expectation outside. So the end result is that I get the expectation of f tilde x minus f star x squared plus expectation summation I from 1 to n wi squared. This is random x now, sigma squared xi. Okay, that's the result I want to prove. So this side is just what I want, as we talked about. And this is what I prove. Okay, that's the bias variance decomposition. Okay, just plug in capital X here and then take the expectation of the entire thing. And so we have this. So neither the bias nor the variance in general is 0. So these estimators are not necessarily unbiased. The bias is just the difference of, the difference of this reconstructed version from there. Questions? So this is what we wanted to prove. Okay. Just exactly this. So maybe pause, see if you guys have any questions. Questions, comments? So this is conditional bias variance decomposition under basically conditioning. So the reason why we use this tail is just so you see that this is just a bias variance decomposition under this new expectation, under this new conditional distribution. And we calculated these two, plug in the random x, take the expectation. Okay. So let me know if you have any questions. Okay. So the first thing we're going to do is deal with this variance. It's easier. Suppose sigma x is bounded. Okay, sigma x can be dependent on x but bounded. So if sigma x is bounded, or the function, this is the conditional variance, which is a function of x. Let's say sigma x is less than or equal to b for all x. How can I bound that quantity? So the variance term, which is this guy, is bounded by what is a simple bound here? Great. Yeah, I'm just going to put it there outside. Inside doesn't matter, but it's just going to be this. Right. This just simplifies everything. Okay, so expectation of the sum of these guys squared. And if you go back to the conditions, unfortunately, you have to. I should have done a better job, probably. So one of the conditions is this. the summation of the weights at the test point converges in L1. What I mean by L1 here means, because they're non-negative, it just means the expectation of summation over I from 1 to n, W and I squared of x. This goes to 0. That's exactly what we have there. So this condition guarantees that that goes to 0. Okay, so this condition E is exactly there to control the variance. Okay, so by assumption, let's say E, yeah, I should have put them here. So this goes to 0 by assumption E. So what if this is not bounded? This is what you're going to do in your homework problem. It's very similar to what we're going to do later in the bias case. So you approximate it by something which is bounded. Okay, but it's a good exercise to do. So the result holds even if sigma is unbounded. But we'll see. Okay. So the classical like regression, sigma x is bounded. Even sigma x is like constant as a function of x. But it's very reasonable to assume that the noise variance is bounded. Not very reasonable, but let's say if, for example, the domain is bounded, it's very reasonable. If it's unbounded, then it's still so like 90% or 95%, I don't know, of the results on regression are the case where this is true. Is it clear so far? Okay, now the tricky part is to deal with this bias. All the other conditions more or less are to control the bias. Because we're not assuming anything about the F star. So you need a lot of conditions. And so that's the discussion of the variance. So we are now gonna focus on the bias there. Okay. So how do we do this? Okay. Let me rewrite the bias. So that's the bias. So bias control. So I have to expand this a little bit. So this was WI x f star xi minus f star x. Okay, I from 1 to n. So what we do is we add and subtract this quantity. Okay, so you're going to add WIX so f star xi is there, right? I'm going to subtract WIX f star divided at x plus WIX f star x minus f star x. So these are inside the sum. So I should put the whole thing squared. Okay. It's just these coordinates do not match. So we add and subtract one that has the two match. This is a very common way of dealing with these things. So if you haven't done any mistake, so you get expectation summation I from 1 to n, WIX f star xi minus f star x. So I'm combining these two terms, plus summation WIX minus 1, I from 1 to n times f star x. This entire thing is squared. So this summation is over all these things and minus f star. So combine these two, you get this combined. So the summation comes over here. F star x is like constant comes out. You get this. Maybe look at this, see if I made any mistake. It's just okay. I'm going to call this GN X. Okay. So what we're going to do is we're going to use this inequality, which hopefully you're familiar with. A squared plus b squared. Okay, so in order to like, this is like a triangle inequality for squares. I want to break this sum into two pieces. But things are squared, but this is like triangle inequality with like a slack. So this thing is going to be lower bounded by twice expectation of the first term is squared, wi x f star xi minus f star x squared plus twice expectation of gnx f star x squared. Okay, you have two terms. And it's just, that's some progress. Okay. So okay, let's first deal with this term. I think in the subsequent slides, I've called this I1, term I1. This is term I2. So I1 is easier to deal with. So I1 is, so first note from one of the conditions, again, you have to go back all the way here. That's a bit of it. So this condition tells me that that Gn is going to 0. And also recall this condition boundedness, which we're going to use. Okay, so going back all the way here, this Gnx is converging in probability to 0 by assumption, I believe. A, B, C, D, probably D, one of them. Okay, so this converges. There's an N here. Converges to 1. That's one of the assumptions. So that assumption takes care of this term in the bias. So this goes to 0 in probability, and this is not enough. So the fact that this converges in probability doesn't mean that this expectation is going to 0. But there's something that I can use. One of the results in like the famous results in probability theory about convergence of integrals. Right? So I note that Gnx converges in probability to 0, and I also have a bound. So this guy is bounded by summation wi x I from 1 to n plus 1, and by assumption this is bounded by d. So this is bounded. So the function, this function, if you look at it, this function squared is bounded by d plus 1 squared f star x squared. And so this is integrable. Okay, so the expectation of this is bounded by the expectation of this, which is finite by assumption. So we're assuming that this regression function has a finite second moment. So this is finite. So I have a sequence of functions. Because this is going to 0 in probability, this implies that this is like a pointwise limit. This implies already that this converges in probability to 0 because f star is constant as a function of n. So this function is going to 0 in probability and is also square integrable. Okay. So, or sorry, it's not a square integrable. So it's dominated basically I should write it a little bit more carefully. If you want, it's dominated by this function, and this function is in L2. Okay, so for all n, basically, this is bounded by this, and this is in L2, so you can use the dominated convergence theorem. Dominated convergence theorem is for when this is almost short, but it also works when this is in probability. I'll let you figure that part out. So by dct, in the end, gnx f star x goes to 0. So this relies on assumption, I believe, E, the boundedness, and probably D, that the sum of the, so you can see that this sum can be different from 1, but this has to go to 1 for this to go to 0. So in order to control this, we need this condition, more or less. And then the rest is technical part of the DCT. But this is fairly simple, okay? Okay. Just do it for yourself. It's just that this sequence is bounded by a function which is integrable. This is not in L2, sorry, this is in L1 because f is in L2. So L1, the expectation exists basically. But then DCT gets you there. Question? You're almost there. Now we get to the really tricky part, which is that part. So this we have called I2, this quantity. Okay, so this is the part where the locality comes in, because I'm evaluating the f star at the same function at xi, and also at all the training points. I want these ways to dampen the effects of all these except the ones that are close to this. So that's the part where the critical issue comes in. Not all weights would work. Okay, so if my weights put all the weights everywhere, then I'm just going to mix these up, and it's not going to work that well. So that's where the locality assumption, which you haven't used so far, comes in, and that just controls this term in the bias. Is it good? Can we move on? Right. Okay. So I'm going to just briefly mention it, and then you fill in the gaps. So if something converges in probability, you can show that conversion probability is equivalent to the sequence conversion probability if for every subsequence there is a subsequence that converges almost short. Okay. So I can pass through that subsequence, let's say. No, that's always true. Okay. And then on that subsequence, so for every subsequence of this, there is a subsequence on which this converges almost shortly, and so this expectation converges on that subsequence. Okay, but then this expectation is deterministic. So any sequence, deterministic sequence for which there is a subsequence, so any deterministic sequence for which every subsequence has a convergence subsequence has a limit. The point is that at this point everything is deterministic, and so there are other proofs as well, but it's a nice little thing which is often not mentioned. Okay, just really technical probability, but it's a good point for you too. You just try to convince yourself by the fact that this has a connection to almost short convergence via subsequences. All good? Move on. Okay, now we're almost there. So how do we bound this? So the point is we pass to the case where f star is continuous with compact support. So use some of the assumptions to effectively reduce to the case where f star has that property. But because the argument is interesting, I'm just going to do it. And this is how you can deal with the unbounded variance as well. So you just pass to something which is continuous and bounded, because the variance is also in L2. Okay, so that's the part that we did already. Okay, so in order to deal with this term, let me rewrite it. So I2 basically is 2 expectation I from 1 to n Wix. Let's see if I made a mistake, hopefully not. Xi minus f star x. The whole thing is squared. Okay, that's this. The first thing that we do is this inequality, which you'll show in your homework problems. It's a consequence of Cauchy-Schwarz. So I have like a summation weights and something here, so that's like AI, and I can bound it like that. Okay. So what I would do is I get the summation of these, which is my assumption bounded by d, plus the absolute value here, and then this guy is squared. Okay, so just look at these. That sort of you get rid of a nice way to get rid of the fact that this is around the entire sum. I just want to move it inside, but I don't want to pay the price that I get this squared. So you can use Cauchy-Schwarz. You get this. This is exactly like coming from this to this, and this is bounded by d by assumption. So that's the first step. Okay, it's like a technical little inequality. This is now where we have to do the reduction. So if things were just, if f star was in continuous and compact, that's my notation, or the usual notation for the space of continuous functions with compact support. So continuous compact support means bounded and closed, right, in RD. So these are functions that are basic. Let's say if you're in R, they're continuous and the support sort of is bounded. So as you go to infinity, like they get 0, right? So they go to 0. Not go to 0, just exactly 0. So anything like this is bounded with compact support. So what we want to do, we want to reduce to that case because that makes our life easier. So what we note is this space also has the property that all the functions are bounded because they're continuous and a closed and bounded set. They have to be bounded and they're also uniformly continuous. Okay, so these are uniformly continuous, bounded, compact support, continuous. They're all good. Very nice functions to work with. They're not still smooth. They could have kinks, but at least they're not discontinuous. And the second sort of thing to note is that these are dense in L2. There's a nice proof in LP, in every LP basically, for P bigger than 1. You can do the proof, like Google. There are very nice proofs of this by the regularity of the measure space. So the idea is that it's just enough to approximate an indicator function, because then indicators go to like combinational linear combinational indicator function called simple functions. They're dense in L2. You just have to be able to say that I can approximate an indicator function, something like that. But the set A could be very, let's say, complicated. The indicator of any set, if I can approximate it, I can approximate linear combinations and linear combinations of simple functions. You can find simple functions, sequence of simple functions that converge to anything in L2. That's very well known, and you can just write simple functions like that. So the main point is to do this, and for this you need some topological regularity. You can sort of approximate a function, like any set from within and outside the compact and open sets. And if the measure space is regular enough, you can do this. And basically, you can imagine I can sort of approximate this by something that's sort of 0 here, just jumps here, and then goes back down. Okay, and then this could sort of start to like get better and better. But it's an interesting real analysis point. I encourage you to look up if you don't know. Okay, so the plan is to reduce it to this case. So what I'm going to do is, so I have f star Oh, there's something missing here. There's F star here. So I'm gonna say that fix some epsilon. Since F star is in L2 and that the space is dense, there exists an edge in this space such that the L2 norm of the difference is less than epsilon. And the L2 norm of the difference, I can write it like that. Okay, so I have this. And then what I'm going to do is I'm going to add and subtract this h evaluated at x and evaluated at xi. Okay, so I'm going to do this. So this difference squared, this is like a triangular inequality. So I'm adding and subtracting basically this term, okay, and this term. So add and subtract h of x and h of xi, and just break it into 3 pieces. And this is like the general, like a plus b plus c squared is less than 3a squared plus b squared plus c squared. Okay. So that's what I'm going to do. The middle thing is the reduction to a function in the CC. The other two are approximation errors. Okay. So, yeah, so that's the, I'm going to tell you. We haven't gotten there yet. So if I do this, if I do summation, if you recall what this is, I'm going to do. Let's see if we can do this. I'm going to sum over wix. Okay. The same sum goes here. So I get summation wix f star x minus h. This is J1. And then J2 would be the other at the end. This guy. So summation wi x h xi minus f star xi squared. And then J3 would be the middle guy, which is the term that we would get if we started with h. So if you look at this, this is exactly the same as this, but with f star replaced with h. So if I just assume that things were in continuous and compact support, I could just have this. These are the approximation prices that I'm paying. Okay, so if I multiply everything by this sum and pass it through, except for the 3 that's there, these are the 3 terms that I get. Okay, so this term is bounded, J1 is bounded by, there's absolute values here as well, because of the Levy absolute value. Okay, so there's the absolute value here. So this is, we're almost done here. This is going to be bounded. This is exactly actually because the x, this doesn't depend on I. So this comes out, right? I get, okay, let's put an expectation as well. So J is also the expectation. We're dealing with the expectation. So expectation of this whole thing. Expectation. So this is going to be expectation f star x. Sorry. Yeah, expectation. Okay, I'm just going to do it once. This thing is constant. It's not dependent on the summation. So this comes out of the summation, and then this guy is bounded almost surely by d. Okay, so what we get is this is less than or equal to d times the expectation of fx minus hx squared. This is just the L2 norm. And by assumption, this is less than epsilon. Okay, this h approximates f star in the L2 norm. For the second guy, what should we use for the second guy? Okay, this is the tricky part. This is some function, right? And then we had that the first condition, the technical condition. I'm going to go back to that. This gives you C times the expectation of h of x minus f star x squared, which is less than d, like C epsilon. The technical condition was you have to accept, because if you want to go back, it's just going to take a lot of slides, but I mean, you can check that this is true. The condition was something like that. This reproduces. So let's go back up and see this. That's the really technical condition, the one that we have here. For any non-negative function, for L function, the expectation reproduces basically the expectation of x. Okay, that's the technical condition. You can see where it comes in. It comes in to deal with this reduction from. Okay, this is not saying we reproduce the expectation of x exactly, but up to a constant. This is good enough because I'm applying it to f here being like h minus f star. So this is some f, like h minus f star squared, okay, applied to xi's. So think of the f as apply with f of x being h of x minus f star x squared. So if you do it, you get just the same function evaluated at x squared, and this is just the L2 norm. So this is bounded by C epsilon. So finally, you're at this point. Okay, let's see. There's also one last thing. So this is the reduction. So this part by approximation, and you can see boundedness and this. So this is bounded by epsilon, and epsilon, we can make it as small as possible. This is the last piece. We still haven't used the locality assumption. Is this so far clear? Sort of. You can go through, like, once you have the statement of the theorem, it's easier to match the conditions. So the last piece, how do we deal with this last piece? So this is a continuous, uniformly continuous function with compact support, bounded, all the nice features, but you're evaluating it at these different points. So now I can use continuity, uniform continuity, okay, to say that when x is close to xi, then h of x has to be close to h of xi. Okay, and the weights have to force me. So these weights have to force me to x. I mean, if these are local, it means that it just picks all the xi's that are close to x, and then h of x would be close to h of xi. Okay, that's the locality part. So let's see how it works. H is uniform continuous. There exists an A such that whenever x minus y is less than A, h of x minus h of y is squared, let's say, is less than epsilon. That's uniform continuity. If I want to like state it as an event, so if you look at this times the indicator function that's less than A, this is either 0, or when this is active, it means that this is less than A, so this has to be less than epsilon. So this is a restatement of this in the event format. Also, H is bounded, so we have this. So it means that if I want to look at this times this indicator, that's the opposite of this. So this is either 0, or when it is 1, I'm just going to bound this by 2 times LS squared, because like you can see that this is like triangle inequality twice this squared plus this squared, 2L times this. Okay, so boundedness gives me that. So what do we want to control? We want to control this. I'm going to control this guy. So what does this do? I just add and subtract, and not add and subtract, just I'm multiplying. I'm going to multiply this, right, by that indicator. So the squared indicator that x minus xi is less than a plus the same thing, right, with the complement. Times the indicator that x minus xi is bigger than a. So this is the bad event. Okay. You can do this because the sum of these two is just 1, right? And now I have this part, which I know is bounded by epsilon, right? This is bounded by epsilon. And this part, which is bounded by 2Ls squared times the indicator of x minus xi, bigger than a. Okay, that's this. The other one is that. So if you followed, this would be bounded by the expectation of so epsilon, expectation of summation I wix plus 2Ls squared summation I wix indicator x minus xi bigger than a. There's an expectation here. 2Ls squared expectation. Okay. So this is exactly the condition that we had. So that's the locality condition. That this goes to 0 is the locality assumption. Assumption, I believe, maybe C, hopefully. So the weights for all the xi's that are away from x by a factor, like by a distance a, the expectation goes to 0. So this I can make it to be less than epsilon if I want for large n, and this is bounded by d. So in the end, the entire thing is bounded by d epsilon times 2L squared epsilon. You put back everything, they were constant, so you get like, just go like count all the we had like I1, I2, just J1, J2, J3. Just put everything together. So everything is like bounded by epsilon, and these are constant. So epsilon was arbitrary. So for large, and you can make it small. Okay. It's not a complicated proof, but it's this last step is technical. And it's interesting where each condition comes in. And you can see controlling the variance is quite easy. Controlling the bias is quite difficult. In the end, what we use is continuity. So you reduce things to continuous functions. And continuous functions, things are local. So if this is close to xi, then these are close, so I don't have to worry about that case. But if x is not close to xi, then my condition is controlled by the weights being small. So the way that we design the local estimator is that the weights away from x are small. So this term is controlled because the weights kill it. This term is controlled because h is continuous. Okay. So h controls that, and this controls this. So we're done. Sounds good. I'm going to post a more detailed version. I have some lecture notes, so you can go through it for yourself. It's a very good exercise. Now let me, in the remaining time, just Okay, so to recap, this is a technical condition for reduction from the general case L2 to compact and continuous, and it controls one of the terms in the bias, right? And I believe this is also coming into play when you have unbounded variance. So the same reduction that we did, you have to do it for the variance. Okay, if you want to do unbounded variance, just reduce it to the case where you have continuous and bounded. This was used throughout. These two control the bias, basically. And this controls the variance. And this is the locality assumption that we're using. Sounds good? Questions? Yeah. Yeah, it could depend on epsilon. Yeah. I see. Okay. Oh, you're saying, I see the point. So let's go. Yeah, it's a good point. So we have an edge. It's close to L2 in epsilon. Then the question is that this L, so this is going to have a support, like it's going to be bounded on the support, but you're saying L would be dependent on epsilon. We can make what smaller? Oh. Good point. Yeah, epsilon is going to be like constant for us throughout because we want to control everything. But so let's say I fix epsilon. The point that Luciano is making is this L that I have is going to depend on the edge and an epsilon because I tried to do that. But yeah, so if I make the yeah, so I can always make A smaller, right? And if I make A smaller, right, probably we can say this is going to be bounded by 1. I can make it be bounded by 1 right? By making A small enough, right? Yeah, I think that makes sense. Or yeah, not 8. So okay, so I think we'll do something like yeah, I think you can do something like this. You pick one such that it's like that, and then you can shrink the support so that the maximum over the support is 1, right? Can it be done? Or is it not possible? Okay, it's a good point. Let's think about it. Maybe you can just post something like our fixed. Yeah, the thing is, yeah, I have to think a bit about it. It's a good point. Okay, let's leave it at that. Just let's go back. Maybe I'll. So for partitioning, I'm going to come back next time and verify. Basically, we're going to verify these 2 conditions. This is too technical. You're welcome to try to like calculate. You can just verify it for indicator functions because then just it goes like, by linearity and limits works for any f. So just, but we're not going to verify this. The main ones are the C and E. So these are the conditions that would give you. So for partitioning estimators, if you have a partition, we saw last time that, so what you do is basically you take some sequences of balls to bound things, and then basically look at all the partition cells that are like intersecting with that ball, and the diameter of those cells. So this Kn is all those that intersect with that ball. The diameter of those at most, like the largest has to go to 0, and the number of cells has to, divided by n has to go to 0. So if you like unpack this, if I take, for example, I can take the balls to be any balls or any sequence of bounded cells that eventually cover the whole space. So let's say I'll take it to be these cubes to the D. If you have a cubic partition of side length Hn, let's say, the diameter would be something like that, would be proportional to Hn. Let's say the dimension is fixed. So it's like if you have a cube of side length Hn, that's the diameter. And so for the maximum diameter to go to 0, the HN has to go to 0. And then the number you can compute by comparing the volume. So the volume, the big ball divided by, this is the volume of each cell. And so this would be roughly like, yeah, so this is going to be like 2R to the D. And this is HN to the D. And so you get 2R to the HN. So basically it scales like 1 over HN to the D. And so if I divide by N, up to constants like 1 over N HN to the D. So we need this to go to infinity. Okay, so the bandwidth has to go to 0, but doesn't have, like, can't go to 0 too fast enough. So this has to be satisfied. So these are the basic conditions. Just one little point is that the exact same thing holds if you have like kernels. This condition holds for the bandwidth of the kernel if it's a boxed kernel. So basically, it's like dominated by the box kernel, which is just the window basically. So it's like between. So the kernel lives between these two guys. It's just reduction basically to the case where you have this box kernel. And then for the K and N, these conditions translate to the number of neighbors going to infinity, and but they can't go to infinity fast, so K over N has to go to 0. So this controls this controls the variance, this controls the bias. Oh, sorry, this controls the variance, this controls the bias. Okay, we'll come back and see. Okay, these are basically the two conditions. One of them is locality, the other is the variance condition. Okay, thank you guys. Come back next time, and I'm gonna try to post the lecture notes so that you can take a look. Okay, see you next time.